Right, so in the previous lecture, we were talking about linear programming. And we show some applications of linear programming, including model predictive control, how to model expansion planning problem. Also, we showed some of the absolute value problem can be modeled as linear programming. So before we talk about the algorithm for linear programming, we would like to talk about something called polyhedral theory. So essentially, polyhedral theory deals with the geometry of describing linear programming problem. Let me show a motivation of why we care about polyhedral theory. Remember, this is a figure in the previous lecture. We talk about the farmer's problem, right? The farmer is thinking about investing in either barley or wheat. And here's the constraints of this problem. It is essentially this region here described by like a polyhedral set, right? But then we observe for this very simple problem, the optimal solution is at a vertex of this problem. Remember, we were showing that here's the contour lines of this problem. Essentially, to find the optimal solution, you are moving upwards with this these contour lines moving towards this direction until you hit a point here that this is the only point feasible for this problem, then that will be the optimal solution. Intuitively, for this problem, the optimal solution is obtained at a vertex, right? So usually in your 2D, we call this a vertex. So in this lecture, we are going to talk about how do you rigorously define what a vertex is mathematically, okay? So an overview of this lecture, we are going to talk about something called polyhedral theory. We will give the mathematical treatment of what is vertices, faces, and rays. Those are some geometric concepts, but they can be described in a mathematical rigorous way as well. And the set we are focusing on is this polyhedral set AX greater than or equal to B. So the reason why we care about those concepts is because those concepts are key in the development of the algorithm for solving linear programming, in this case, the simplex algorithm. In the meantime, we will also show that the optimal solution of a linear program is always at a vertex, okay? So first of all, to start with, let's define what is a polyhedral set, right? So usually without loss of generality, we can denote a polyhedral set by AX greater than or equal to B. So here A is M by N matrix and B is a vector of dimension Rn. In other words, you can think about a polyhedral set of M linear inequality constraints, and they are written as matrix AX greater than or equal to B. And we talk about linear programming can be represented in different form. Of course, you can do AX greater than or equal to B, and without loss of generality, you can also represent a polyhedral set as AX less than or equal to B. And we also talk about linear programming can be represented in the so-called standard form, right? We showed, how do you convert a generic linear program to the standard form by adding things like slack variables. Then you convert it to a linear equality constraints, and all the inequality constraints are X greater than or equal to 0. A very interesting fact is that when we talk about a polyhedral set, it can be either bounded or unbounded. Here's very two simple examples, right? So let's say we are in 2 dimension, the x-axis is x1, the y-axis is x2 here. Then for the left problem, we have 3 constraints, x1 greater than or equal to 0, x2 greater than or equal to 0, and x1 plus x2 less than or equal to 2, right? So if you look at the figure here, it's representing this shaded area here, and it's a bounded region, right? On the other hand, if we remove this constraint x1 plus x2 less than or equal to 2, then the right-hand side is still a polyhedral set here, but it's unbounded. Basically, it describes the first authent of the problem here. Okay. By the way, feel free to stop me if you have any questions. I cannot see whether you are raising your hand or not, so feel free to interrupt me at any time. So with that, let's start building up the polyhedral theory. So let's first define two concepts that are essential to polyhedral theory. The first one is this set X that are constrained by a single linear equality constraint, A transpose X. So here A is a n-dimensional vector, X is an n-dimensional vector, B is a scalar here, right? So this equality constraint is called a hyperplane. If you look at it in 2D, think about this as a linear equality constraint. For example, you can let's just write something like x1 plus x2 equals to 1, things of that sort. It is describing a hyperplane, which is basically a straight line in 2D. In 3D, you can think about the hyperplane is a two-dimension thing, like a hyperplane, right? And if we replace the equality with an inequality, that will be A transpose X greater than or equal to B, it is describing a half space. Instead of this line here, you can think about the half space is all the regions that is below the plane if we have A transpose S less than or equal to B here. Okay. Okay, any questions so far? All right. So if no questions, let's talk about a very important concept here. It's called an extreme point. So how to define an extreme point? If you read the definition, it says if a vector in the polyhedral set is an extreme point, if we cannot find two distinct vectors y and z and a scalar lambda such that x is a convex combination of y and z, right? In other words, if a point x cannot be expressed as a convex combination of two other points in P, then it is called an extreme point. Okay, so intuitively, if you look at this picture in 2D, essentially extreme points are the vertices of this polyhedral set, right? So at these points A, B, C, D, and E, those are the vertices. It cannot be expressed as two distinct points in the polyhedral P, right? For example, let's pick a point C here. Of course, it can be expressed as two distinct points that are outside this polyhedral. But then if you want to express as 2 points within this polyhedral, it's not possible, right? If you pick an arbitrary point and want to express C as a convex combination, you will go outside this polyhedral. So that's why C is an extreme point here. On the other hand, if you look at this point, F, that is within the polyhedral, it is clearly not an extreme point because you can express F as a convex combination of these 2 points H and G, right? It lives within a line segment of this line segment H and G. So that's a definition of an extreme point. Okay. And then what is a vertex? Intuitively in 2D, it's very easy to check. If I give you a polyhedral, you can tell me that those 5 points are the vertices. But how to define it in a mathematical rigorous way? So here it gives a definition. So let P be a polyhedral set. And then let's say we pick a point X star in P. It is called a vertex if you can find a hyperplane that separate x from the rest of the polyhedron. So if you read this definition clearly, that will be if there exists a vector C such that C transpose X star is strictly less than C transpose X for all the X satisfying X is in the polyhedral set P, except on this particular point, X star. Okay, so this algebraic definition may not be that intuitive, but if you look at this figure, it's very easy to show. So let's say this is a point, X star, right? And this is the hyperplane described by the vector C. So the C is in this direction, and then the hyperplane is this hyperplane here. So as you can see, C transpose X star, of course, is equal to X star here. But all this polyhedral is on one side of this hyperplane, except on this point X star here. Okay, so essentially you find a hyperplane that only intersect with the polyhedral at a given point X star, and the rest of the polyhedral is all on a single side of this hyperplane. That's what a rigorous definition of a vertex is. Okay. And as you can imagine intuitively, a vertex is equivalent to an extreme point, right? Because if we are going to express things in words, they are both like vertices, right? Although their mathematical definitions are different. But on the other hand, just using the definition of the vertex and the extreme point, here's a comment. It is very hard to verify whether a point is an extreme point or a vertex just using their definitions, right? Because if you look at the definition of an extreme points, if you want to check whether a point is an extreme point or not, then you have to argue that there does not exist 2 points that are convex. There does not exist 2 points whose convex combination would be equal to this point, right? It's very hard to verify there does not exist in a very easy way. And also, if you are going to use the definition of the vertex, it's also very hard to verify because you need to find a hyperplane, right? And the hyperplane may not be so trivial to find. Okay. So with this motivation in mind, we need another characterization of an extreme point or vertex that are easier to verify. Okay. So that is something called a basic feasible solutions. Then before we introduce what is a basic feasible solution, we need to define something called active constraints in a polyhedral set. Okay. So here, let's define active constraints. So let's suppose we have a polyhedral set P that are defined as a bunch of linear inequality constraints, AX greater than equal to B. We see that the corresponding constraints, let's say A sub I transpose S greater than equal to BI is the ith constraint among all the M constraints we have. We see this constraint is active, or in other words, it is binding if AI transpose X star equals to BI, right? This definition is very intuitive because this is an inequality constraint. We say it's active if the equality hold at a particular point X star. That is called an active constraint. So here's an easy way of illustrating what is an active constraint. suppose we are looking at this point A here. As you can see, the active constraint at the point A are these two constraints here. If you are going to write them as A2x greater than equal to B2 and A1 transpose x greater than equal to B1. Okay. So this figure shows that at this extreme points A, two of the inequality constraints, right? So this inequality constraint is showing we have to be at this type side of the region, and this inequality constraint is constraining the polyhedron to be at this side of the region here, right? And at point A, two of those inequality constraints are held as equality constraints, right? So this is an example in 2D. As you can imagine, if we want to uniquely define a vertex in n-dimensional, maybe we need n linearly independent constraints to uniquely define a point, right? And then because you have n linearly inequality constraints, so there is a typo here. This should be AI transpose X equals to BI. If we have n linear inequality constraints, then we can uniquely define a point. Okay. Any questions for the motivation here? Okay. So now with this motivation, we can define something called a basic solution and basic feasible solution. Okay, so if we say X star is a basic solution, if the following holds. Of course, we need to satisfy all the equality constraints, right? If maybe AX greater than equal to B has some implicit equality constraints. So we say all the equality constraints are active, and out of the constraints that are active at X star, and there are n of them that are linearly independent. So with n linearly independent active constraints, you can think about this as n linearly independent equalities. Then we are guaranteed to have a unique solution, right? This is a simple result from linear algebra. If you have constraint AI transpose X greater than equal to BI, and there are n of them for I, let's say we pick n of them without loss of generality, that's just assume it's the first n of those constraints, right? And then if we have n linearly independent linear equality constraints, there can only be a unique solution to these linear systems, right? You take the inverse of this matrix and multiply them by B. Okay, so that's the basic solution, right? So remember in the basic solution, we are kind of arbitrarily picking a linearly independent constraint that does not guarantee all the other linear inequality constraints we did not pick are satisfied. Okay, so supposedly, let's say those are the n linearly equality constraints. And then there are some other constraints that say A transpose IX greater than equal to BI. Those are inequality constraints that say I from n plus 1 all the way to m. If the solution of this linear system also satisfy all the other linear inequality constraints, then that means this is a feasible solution, right? So that's a definition of a basic feasible solution. If the basic solution satisfy all of the constraints, right, like those linear inequality constraints as well, then we see it is a basic feasible solution. Okay, so to summarize, we have introduced the three main concepts. A basic feasible solution is you pick n linear equality constraints, make them active, then that is a basic solution. If they happen to be feasible, that is a basic feasible solution. And we talk about the definition of a vertex. which means if you can find a hyperplane that hit the polyhedron only at one point, and the rest of the polyhedron is in the other side of this hyperplane, then this point you hit by the hyperplane is a vertex. Then we talk about extreme points, right? If you cannot find 2 points that the convex combination of 2 points is this particular point you care about, then that point is an extreme point. Okay, so intuitively you would expect all the 3 definitions are the same. Okay. So again, maybe before we talk about why the 3 definitions are the same, we can kind of explain using this problem, what is a basic solution and what is a basic feasible solution here. So here, let's assume we have a bunch of linear inequality constraints, and then they define this shaded area here. So as you can see, the point A is a basic solution because it is defined by 2 active constraints. The crossing of these 2 active constraints defines A, but A is not a feasible point to the polyhedron. So that's why A is a basic solution, but not a basic feasible solution. On the other hand, if you look at points E, D, C, and F, they are the basic feasible solution. And similarly, B is a basic solution, but not a basic feasible solution. Okay. Okay, so here's one of the main theorem of this this lecture. Let P be a non-empty polyhedral set, and let X star is a point in P. Then the following statements are equivalent. X is a vertex, X is an extreme point, X is a basic feasible solution. So all the 3 statements are actually equivalent. And among all the 3 statements, I would argue that the definition of basic feasible solution is the easiest to check. Right? Why that is the case? Because if you want to find a basic feasible solution, you just pick n of the constraints to be active and solve for the n linear inequalities, linear equalities that gives you a unique solution, right? And then you can immediately find whether that is a basic feasible solution or not. If it is a basic feasible solution, these theorems also tell you it is an extreme point, it is also a vertex. Any questions related to interpreting this theorem? Okay, I guess we because it's a Zoom lecture, we don't have as many questions as before, but please feel free to ask questions if anything is not clear. Okay, so I'm not going to show the proof. If we have some time towards the end of the lecture, I will probably show the proof of this theorem. Okay, so with these theorems, there are some corollaries that we can derive. Okay, so since a way to choose extreme points, vertex, and basic feasible solution is by picking n of the active constraints out of the m constraints, right? So with this definition, we can show that the number of extreme points, vertices, and basic feasible solution is finite, and it is upper bounded by m choose n, right? Because you can only choose, there are m choose n different ways of picking n active constraints out of the m constraints. That's the first corollary we can immediately derive. And then the other corollary we can derive is that by definition, if a non-empty polyhedron has extreme points, if and only if you can find n linearly independent vectors out of the m constraints coefficients. That's just the definition of an extreme point. So with that, I'm going to introduce another concept that are causing some numerical issues for software developers. And it is also related to the simplex algorithm. This concept is called degeneracy. So what does it mean to be, for basic solution to be degenerate? Okay. So degeneracy means that if at a basic solution X, if more than n of the constraints are active at X, then we said this solution here is degenerate. So what does it mean? If we look at this, let's say if we first look at this problem in 2-dimension, right? Remember in 2D, in order to find uniquely define a basic feasible solution, we only need 2 linear equality, right? So if you look at this point here, for example, it is intersected by 2 linear equality, right? So this point is not degenerate. On the other hand, if you look at this point D here, it is intersected by 3 equalities here, right? But this problem is in 2D. So if the problem is in 2D, and at this given point, 3 constraints are active, then we say this point D is a degenerate solution. Okay, and similarly, for this point C, 3 constraints are active, right? This is 1, 2, and 3. 3 constraints are active. Then this point C is also a degenerate basic feasible solution. Actually. Okay. So degeneracy is kind of usually it happens by coincidence, right? So if you 2 constraints already uniquely define this point, and it happens to be the case that 1 more constraints are also active. As you can see, this particular constraint is actually redundant for this polyhedron. We just add this constraint to make a degenerate solution. Okay. And then here's a problem in 3D that also explains what happens in 3D. Imagine in 3D, we need 3 equality constraints to uniquely define a solution. For example, if you look at this point B here, it is uniquely defined by 3 hyperplanes, right? So you can see this point B is defined by, this is the first hyperplane, this is the second hyperplane, and this is the third hyperplane that are defining the point B. But on the other hand, if you look at this point A here, it is defined by, this is the first hyperplane, this is the second, and this is the third hyperplane, this is the fourth hyperplane here. So 4 hyperplane are active at the point A. So in other words, A is also a degenerate basic solution. Okay. Any doubts for the definition of degeneracy? Okay. So let's apply degeneracy in a special case. If we are talking about the standard form polyhedron, we have constraints AX equal to B x greater than equal to 0, and let that x be a basic solution. Okay. M be the number of rows in A. So the vector x is a degenerate basic solution if and only if more than n minus m of the components are 0. Okay. So remember the definition of degeneracy is that if the vector x is n dimension, they are more than n linear constraints that are active. So if the polyhedron is in standard form, we already have m constraints that are equality constraints. They must hold, right? So we already have m constraints that are already hold, and then all the rest of the constraints are x greater than equal to 0. So in that case, if we want to get a degenerate solution, then we need more than n minus m of those x to be 0, such that we can have more than n active constraints. Okay, so this concept will be used when we are developing the simplex algorithm. All right, so if there's no question, let's move on to talk about a different concept called phases.
I had a quick question, if that's okay.
Yeah, sure, please.
So on that last point, is that basically the same thing as just saying that like you're over constrained?
Yeah, it's kind of you at a given point, you have more than n constraints that are active, right? This is a so you can think about this slide is a generic definition, right? If there are more than n active constraints that are active, but if this point is still feasible, then I wouldn't say it's kind of like over constraint. It's more like you pick two active constraints, and your third constraint happen to hit this point, right? If you perturb your third constraint a little bit, then you will not have any degenerate point. It's more like by coincidence, the three constraints you define happen to cross the same point. I would think about it like this. But then if in the standard form, you can use the same definition since you already have m active constraints, since they are equality constraints, they must hold. And then you need more than n active constraint, right? You already have m constraints, then you should add another n minus m constraints, right? So if they are more than n minus 1 of the x being 0, that means more than n minus m of those constraints are active. So in total, you have more than n active constraints. I don't know if that answers your question.
No, that does. Thank you.
Okay. All right. Other questions? Sure. All right. So let's talk about a different concept called phase. So a phase of the non-empty polyhedral P is a non-empty subset of P, where a subset of the inequalities are active. In other words, you can pick a subset of the inequalities and force them to hold as equalities. Then that is called a phase. So here are some examples of phases. The polyhedral set P itself is a phase. If you pick an empty set of inequalities, right? So no inequalities are active. Then you basically reproduce the set P. An extreme point is also a phase because you can pick unlinearly independent inequalities and they are active. That defines an extreme point. So that's why an extreme point is a phase. And those edges in this figure, they are also the phases of a polyhedral set. If you look at this this line segment ED, it is a face because one single inequality hold as active constraint on this face ED. And similarly, the DC is also a face of the polyhedral set. Okay, so the face will be a very important concept in integer programming, but in linear programming, it is also something you should also know. Okay, so now I'm going to switch gears and talk about something called a polyhedral cone. So remember, we have defined what is a cone in our second lecture when we talk about convex sets, right? So just to refresh your memory, a set C is a cone if you pick any point in this set C, and lambda C is also, lambda X is also in C. And this has to hold for any lambda greater than or equal to 0. Okay. And then a polyhedral cone can be expressed in this form. Okay, so a polyhedral cone can be expressed in this form, AX greater than or equal to 0. So why this is a cone, you can check the definition. So let's suppose we pick any X for all X such that AX is greater than or equal to 0. And then if X is greater than AX is greater than or equal to 0, then you can easily see that for all lambda that are greater than 0, then lambda X also satisfy this inequality constraints, right? Because lambda is a non-negative number. If you multiply X by lambda, this inequality still hold, right? So that satisfies the definition of being a cone. Now let's look at at a very simple example here with 2 dimension, right? So this problem is x1 greater than or equal to 0, x2 greater than or equal to 0. I mean, of course you can express it into this form: ax greater than 0. It's just the first element. A1 is nothing but 1, 0, and A2 is 0, 1, right? So that is in this form of a polyhedral cone. And intuitively, if you pick any point in this cone, you can show that lambda x, let's say if we call this point x, as you can see, lambda x is also in this cone, right? The lambda x is essentially this ray here, right? Lambda is greater than or equal to 0. And of course, this lambda x is still in the first orthant, right? That's just an example of being a polyhedral cone. Now we are going to define a few other geometric concepts, including race and the recession cone. Okay, so let's define what that is. So if you look at this polyhedral set defined by AX greater than or equal to B, let us pick some point Y that is in the polyhedron. And then we define the recession cone at a given point Y as a set of the directions D along which we can move indefinitely away from Y without leaving the set P. More formally, the recession cone at a given point is defined as follows. Suppose you have a point Y, and then what you said is you can move along this direction D indefinitely. Indefinitely means you can pick any lambda that lambda is greater than or equal to 0. That means you start from this point Y, and then you move towards direction D indefinitely with lambda be any non-negative number here. Okay, so this is the figure to demonstrate what is a recession cone. Okay, supposedly the y we pick is at this particular point. And then as you can see, the recession cone is essentially any of the rays between this vector here and this vector here, right? Because when you move along this vector, the first vector is parallel to the boundary here, right? So if you move along this direction, because it is parallel to the boundary at the left, it will never hit the boundary, right? And then the other extreme direction is parallel to the boundary on the bottom, right? So if it's parallel, it will never cross the boundary at the bottom. And any of the directions within these two extreme directions, they belong to the recession cone at this particular point here. And if we pick a different point, you can also draw the recession cone. Essentially, you find out for this problem, no matter which point you pick, the recession cone is essentially the same, because the two extreme directions are one direction parallel to this boundary here. The other extreme direction has to be parallel to the direction at the bottom. If it is not parallel to the direction, if you go indefinitely, they will always cross with each other. Okay, that's intuitively how we view the recession cone. Any questions here? All right. So then if you buy that, then we are going to derive algebraically how to express the recession cone. Okay. So I'm going to argue that the recession cone is exactly this set AD greater than or equal to 0. Okay. So why that is the case? So first of all, as you can observe, for all the directions that satisfy AD greater than 0, it is part of the recession cone, right? Because remember the definition of the recession cone is the following. First, you have a point y. So you have a point y, and y is a point in the polyhedron. So ay must be greater than or equal to b, right? So because y is a point in the polyhedron. Okay. So if you add a point d such that AD greater than or equal to 0, I'm going to argue that if D satisfy this constraint, you can always go along this direction D indefinitely, right? So in other words, we need to argue that when D satisfy this constraint, this inequality must hold. Why that is the case, it is very simple to show, right? Because you already have ay greater than or equal to b. So ay, we only need to show ay plus lambda d has to be greater than or equal to b, right? And since ay greater than or equal to b hold, also ad greater than or equal to 0, it is okay, very easy to show that this constraint must hold. Okay, so that kind of shows that when this constraint, when D is in this cone here, it is a part of the recession cone. Now we have to show that if D violates this constraint, it will not be in the recession cone. Okay. So in order to show that, you can argue by contradiction. Let's suppose there exists one element of this this inequality constraints such that supposedly it is a S constraints. Suppose the contrary is true if AI transpose D less than or equal to 0. Then if you add AI transpose D to the original constraint and make it go along this direction D indefinitely, it will always violate the original constraints. Okay, so that's why we must have this constraint satisfied. Okay. This also shows that the recession cone is independent of the starting point of Y, because if you look at this expression here, it is independent of the starting point Y. Okay. And the non-zero element of the recession cone are called the rays of a polyhedron cone. Okay. Any questions here? All right. So now we are going to define a concept called extreme rays. So we define a vector D. It is called an extreme ray of a cone if there do not exist linearly independent U and V and positive scalars such that D can be expressed as a linear combinations of U and V. Okay, if you look at this 2D example, you can see that these two arrows here are the extreme rays of the recession cone because they cannot be expressed as the linear combination of two other rays. On the other hand, if you look at the rays that are within the two extreme rays, they can be expressed as linear combination of the two extreme rays. Okay. Now then the next theorem will tell us how do we identify the extreme rays from a polyhedral set. Okay. So here it says if we want to find the extreme rays for a given polyhedron cone here, AX greater than or equal to 0 for some A. In order to find the extreme rays, we should take a subset of those linear inequalities. Supposedly the subset is defined as A superscript equal. Supposedly the subtype is A superscript equal X equal to 0. This subset denote the active constraints at direction D. So the theorem is saying D is an extreme ray of C if and only if the rank of this matrix is n-1. Okay. So as you can see, the difference between extreme ray and extreme points are the following. When we are finding extreme points, when we need n-linearly independent active constraints, right? And when we are finding extreme rays, we need n-1 linearly independent active constraints. Okay, so let's show a trivial example to say why this theorem is true. Supposedly we are dealing with the non-negative authent x1 greater than or equal to 0 and x2 greater than or equal to 0. Okay, right? So we are talking about this particular set here. And it's very clear that the extreme ray for this non-negative authentic cone is this direction and this direction, right? And maybe let's use this theorem to reproduce this result here. Okay. First of all, let's realize that we are in 2D, right? So n is equal to 2, and n minus 1 is 1. N minus 1 is 1. So we only need to pick one active constraint, right? So let's first pick the first the first active constraint. Okay, so in other words, the first extreme ray is derived from x1 is equal to 0. Okay, and we need a non-zero vector that satisfies this constraint. Then the non-zero vector would be x1 and x2 equal to 0, 1, right? And this direction clearly satisfies this constraint here. And when with that, we get the extreme ray in this direction, essentially this point, this direction here. Okay. And the second extreme rays can be found by enforcing the second constraint, x2 equal to 0. Then the direction would be x1, x2 equals to 1, 0, right? We need a non-zero vector that satisfies the constraint ax greater than equal to 0. Okay. And then we kind of reproduce this extreme ray here. Okay. Any questions here? Okay, so I'm going to skip the proof for now. If we have time, I will come back to the proof. Okay, so here we are going to talk about something called Minkowski-Weld theorem. If there is one thing you should remember from this lecture, I would say that will be this theorem. If you want to pick one theorem you want to remember within the whole linear programming class, I would still say I will try to remember this theorem here. So let's try to talk about this theorem. So it's that if a polyhedral P, for any polyhedral P, it can be expressed as the following. Okay, so we first define the set Vk. Vk is a set of extreme points of P. And we also define some vectors Rj. Rj is a set of extreme rays of P. We already talked about how to calculate the extreme points and the extreme rays. Now, after you got the extreme points and the extreme rays, as you can see here, any polyhedral P can be represented as, so this is a convex combination of all the extreme points. So here, all the lambda sum to 1 and all the lambda greater than or equal to 0. Okay, so the first part is a convex combination of extreme points. And the second part here is a so-called conic combination of extreme rays. So here, the mu j's are greater than or equal to 0, right? So that is called a conic combination. So if we are going to say Minkowski-Weld theorem in words, is that a polyhedral can be represented as, this is so-called a Minkowski sum of the convex hull of its extreme points and the conic hull of its extreme rays. Okay, so what is Minkowski sum? Minkowski sum is if you pick two sets A and B, the Minkowski sum of set A and B is you pick a point in A and pick an arbitrary point in B, and then calculate A plus B, right? So this set is you pick all the points, any of the points in A, pick any of the points in B, and you take their sum, right? This is essentially what the first part is a convex hull of the extreme points. The second part is a conic hull of all the extreme rays. Okay. Is this theorems clear for people? Okay. So if it's clear, we are going to show some corollaries for this Minkowski well. The first corollary is the following: if the polyhedron is bounded, then it is a convex hull of its extreme points, right? So why that is the case? Because if a polyhedron is bounded, and it does not have any extreme rays, right? If it has an extreme rays, you can go infinitely towards the direction of the extreme ray, right? So if a polyhedron is bounded, it doesn't have any extreme rays, then the only thing we have is a convex hull of the extreme points here. So here's another corollary, which is very useful in practice. If we consider a problem over a pointed polyhedral cone, then the optimal cost is equal to minus infinity if and only if there exists some extreme ray D such that C transpose D is negative. Okay. So why that is the case? Because a polyhedral, this polyhedral cone can be expressed as a conic combination of all the extreme rays Rj, right? Mu j greater than or equal to 0. Then if we know that it's infinity, there must exist some point such that C transpose this point goes to infinity, negative infinity. In other words, there must exist at least one of the Rj such that it has a strictly negative product with C. Okay. And we can also talk about another corollary, which is the fundamental for developing the simplex algorithm. So that says if we are minimizing and this polyhedral set is non-empty and the optimal objective value is not negative infinity, then the optimal solution can always be obtained at an extreme point. So why that is the case? Because due to Minkowski well, a polyhedral is a convex combination of the extreme points and a conic combination of extreme rays. So if we say that the optimal cost is not infinity, we must have the C transpose Rj greater than or equal to 0. The reason is that if any of the C transpose Rj is strictly negative, then this objective would be negative infinity, right? Because you can just go along this extreme ray direction to get an negative infinity solution. Okay, so with that being positive, then at the optimal solution, since we are minimizing, all the mu j's must be 0, right? Because this is non-negative. We can just set the mu j to 0. And then we can always pick one extreme point that minimize C transpose Vk, right? So if the extreme rays all have positive product with C, then the rest of the problem is nothing but C transpose summation over lambda K weight K, right? That's a convex combination of all the extreme points. Because the lambda has to be sum up into 1, right? So we can always pick the extreme point such that C transpose Vk is minimized. Then we suppose K star minimizes C transpose Vk. Then we can just set lambda K star equals to 1. And all the lambda K equal to 0 for K is not K star. In other words, if we can find the extreme point that maximize C transpose Vk, we should put all the weight of lambda on this particular extreme point. Okay, that is to say, there always exists an extreme point that is the optimal solution for the linear programming problem. Okay, this is a very important result. We are going to use this for building the simplex method. Any questions here? Okay, so that's everything I would like to talk about for this lecture. Maybe let me pause for 1 minute to see if there are any follow-up questions you can ask. Okay, so if not, I would like to talk briefly about a problem in homework 3, which we did not have time to talk about in lecture. We haven't released homework 3 yet, but this will be one of the problem in homework 3. Especially for a student whose major is not in chemistry, this might not be familiar, but this is a very good exercise. This is like the most common optimization problem chemical engineers have solved so far, related to heat exchangers. So what is a heat exchanger? A heat exchanger means in the chemical plant, you may have some hot stream you want to cool down. For example, you can represent a stream. So let's say in this case, H1 is a hot stream. You want to cool down H1 from 400 degrees C to 120 degrees C. Okay. That is some stream you want to reduce the temperature. Of course, if you want to reduce the temperature of a stream, one of the options you can do in a chemical plant is to use some cooling water to cool down the hot stream. Okay. And there are also some cold stream you like to increase the temperature. For example, in this table, there is a stream called C1. The original temperature of C1 is 100 degrees C. You want to increase the temperature of C1 to 250 degrees C. Okay. Okay. So one of the options to increase the temperature of the stream is to use some heating mechanism. For example, you can produce some high pressure steam. Of course, if you want to produce high pressure steam, you need to burn some fossil fuels like natural gas or oil, right? But besides just using the cooling water or the steam, as you can see here in this problem, the steam is at 500 degrees C. Of course, you can use the steam at 500 degrees C to heat this cold stream from 100 degrees C to 250 degrees C. And the cooling water temperature is at 20 to 30 degrees C. It is easy to see that you can use the cooling water to cool down the hot stream from 400 degrees C to 120 degrees C. Of course, buying those steam and cooling water will cost money. And one of the inventions in chemical engineering is to have something called heat exchangers. So you can have a heat exchanger that can exchange heat between the hot stream and the cold stream instead of using the steam or cooling water. For example, in this case, the hot stream H1, since its temperature is higher than the cold stream C1, it is hot enough to heat the cold stream 1 from 100 degrees C to 250 degrees C. If you assume you have enough hot stream. Okay, so how do we know we have enough hot stream or not? So here in this, in the first column, it shows the energy you need in order to increase hot stream by 1 Celsius, right? So this means you need 1 megawatt energy to increase the to decrease the temperature of H1 for 1 degree C, and similarly, we have this value for all the other streams. So it is kind of related to the heat capacity of a given stream, right? And the quantity for sure. Okay. So the idea of this heat exchanger problem is, how do we design a heat exchanger network such that the heat can be exchanged in a cost optimal way, right? Then you can reduce your consumption of energy just by matching your hot stream with some of the hot stream, with a cold stream, to reduce the cost of steam and cooling water. And here, there's another concept called minimum recovery approach temperature. Maybe chemical engineers are familiar with this. But this actually means in order for the hot stream and the cold stream to exchange heat, the temperature of the hot stream has to be greater than the temperature of the cold stream plus HRAT. That will be 20 degrees Celsius here. Okay. Any questions so far here? Now with that, this exercise problem can kind of help you to formulate this linear programming model for design the heat exchanger network. First of all, we draw something called the temperature interval. So here's the temperature interval. We have the temperature for each of the interval. Then you can put the hot, for example, the hot stream is from 400 degrees C to 120 degree, and then H2 is from 340 to 120. And on the other side, we have the cold stream. Their temperatures are moving up. So the linear programming model is a so-called transshipment model. It will decide how the energy will flow among the hot stream and the cold stream, and which can be seen in the next figure here. So here's how the heat cascade will flow around this diagram here. So the 1, 2, 3, 4 denote the temperature, the temperature interval. And here's the heat H1 have to lose in this temperature interval. And similarly, in temperature interval 3, those are the energy H1 need to lose. What you need to do is to formulate a linear programming model such that you need to do a heat balance at each of these intervals. Then the input from the hot stream to the this is so-called the residual heat from the previous interval, because any of the heat from the previous interval can also heat the colder stream. Okay, so with that, you can do a mass balance, meaning that the input from the hot stream and then the residual heat has to be equal to the heat out of the interval. Okay, that's essentially the idea of this homework problem. And we will put a reference. You can also read this homework problem in detail in one of the textbooks. All right, that's all I want to talk about today. Any questions?